being a material scientist, we are a bit diverse. We work in various areas, but I will today just give you two examples. And I just want it to be very light-hearted, interactive. Just feel free to ask question anytime. You don't have to wait till the end. So I think when I got the invitation, and most of the time you accept the invitation and then you forget it. Then you start preparing your talk few days, and then I looked at the legacy of these conference open readings. Beautiful name, and also so I saw all the speakers. They have talked very much about general things which should be of concern to everybody, not only a chemistry student but physics student, engineering, and so on. So I will today touch upon few things. One is why materials innovation is so important when you look at health and energy transition, and I will just give two examples. They will relate to advanced ceramics, both as powders and coatings, because ceramics are needed for everything you do, and I think all these sustainable transition is ultimately a transition of material science, right? Yesterday I had a very nice discussion with Professor Kareva's sons, and they were saying, so actually the technology is getting old because material scientists are responsible. It was in a lighter way meant. What he was saying is why a material has to have a lifetime of only 2 years or 3 years in most of the electronic gadgets. What is it? Is it a marketing, or is it that the material don't have that resilience? And that's something we have to engineer, and that can be engineered. It's never about the functionality, it's also about the durability. And I will briefly talk about that. The small molecules that we see all around us, can we use them as our energy source? One thing that is very concrete is the new type of drug delivery application. If you look around, the amount of antibiotics that is coming in the sewage, from the hospitals, in the water, everybody is over-medicated nowadays because a lot of things you can take by yourself, all the supplements and many things that is happening. So we need new paradigms in terms of processing materials for a better and more efficient pathway to make the same material efficient. It's not about discovering. We have a lot of materials. We don't need to discover new. We have to make those that are known better. So I will talk about some new processing techniques. And if you look around, we are living in a world which is driven totally by speed. So everything is just increasing, right? So whether you look at the number of transistors that you can put on a micro chip, it's just exponentially. We all know the Moore's law, even if it is not a law, but we know that there's an exponential growth here. We know that this is due to the efficiency, and also that the fact that a lot of people are using electronic gadgets. So the world population is contributing to it. Accordingly, the energy demand, if the population is growing, the energy demand goes up. Even scientific publication, way more publications are coming. I don't think that we have produced the same number of scientists, but the publication speed has gone up. So that is also amazing, right? So this is, and we have to put in context, nobody is reading anyone's paper nowadays. So I think this is also a kind of, we just wait how long this is going to continue, because it's a business model now. It's becoming a business model. It's not always, you don't have time to verify that somebody has published the same data somewhere else. So I think all these things are, and obviously through the globalization, one thing that our nature has suffered, our planet, is the biodiversity that has gone down. So obviously it's fine to have now all the fruits and all the vegetables all through the year, but obviously it reduces the biodiversity of the local regional surroundings. And obviously this big challenge of global temperature of our Earth's surface going about 1.5 degree, many people may ignore climate change just by an executive order, but that's not true. If you look around, and I have lived in India, we used to play in April when I was a kid outside, but today it's 40 plus degrees now already in April. And in May, June, it will go 50 plus. So it's very big problem for older people. And I can relate it. My father is 91, he lives alone. So if he has to leave even his house, 50 plus degrees is too much for an old person. So I think these exponential challenges are due to this demand, and we see this. I mean, you come to this beautiful new campus, what you see is buildings, new buildings. Everywhere is going on, and we need this because we have to make sure that our surroundings are maintained. So the biosphere that has given to us, we have, for good reason, we have converted into a technosphere. It's no longer a biosphere. Why it's a technosphere? Because the amount of man-made goods that we have engineered, that's steel, concrete, is more than what we have from the nature. So, and it's not long back, 5 years back, the threshold was overcome. In 2020, we crossed the limit when the biomass was less than the engineered good. So today we have a technosphere around us. So you can say, so what? It's good, it's showing us the progress. The problem is now the equilibrium is shifting, right? As long as it was biomass and engineered goods and there was a dynamic equilibrium, it's fine. And if it is not there, obviously we will have the big challenge. And the challenge is that everything that we have on our planet is limited. So I always say that's the mono layer of life. Our entire life is in the top 30, 40 meters of the earth crust, right? All the resources, everything is located here. So in this zone where you have all the minerals, water, everything that is needed, even graphite for the battery, this is here. You compare it with the graphene, and I was inspired. I asked Professor Kareva whether this is the inspiration of this building, that you have graphene here. And it's again, it's a wonderful material, and there are many other materials which are two-dimensional. That's a way, if you can enhance the functionality and reduce the amount that is needed, if you reduce the amount of atoms that are needed to achieve a certain functionality, to make a sensor or to electronic device, then you are helping the resources. So why I'm telling this? Because if you look around, we are having planetary boundaries, because this is what you see in this, that there is a limited or finite resources. And if we are crossing those limits, then we are breaching the planetary boundaries. And there are at least 9 planetary boundaries. It started with the report of Club of Rome, and now there is an institute in Berlin with which we are working. They are every year telling us which of these, and I just picked these 2, because climate change is obviously the energy demand. I mean, you are coming to this place, if you're not driving a cycle, you're using a car, you need some source of energy. Even if you're driving an electric car, you need energy. Materials are needed. For all the construction, cement and steel. We can talk about magazines and MOFs, but ultimately mankind needs steel and cement. And these are energy intensive, CO2 intensive industries. Freshwater use, because a lot of people are thinking all these recycling and all the words with refurbishing, repurposing, redesigning, rethinking, they need a lot of resources. Water. So if you are looking at the electronic gadgets that you can recycle, you need a lot of fresh water. For refining, mining, if you need more and more. So that is, again, one of the planetary boundaries which is then restricting our growth. So in this exponential age, and I brought this story with me because I thought there are a lot of young minds here. This is an old Indian story that there was in a village, a king, he was playing chess, and whoever was winning against king was allowed to ask for whatever he or she wants. So there was a modest person playing with him, and then he won the chess game, and the king said, okay, you can ask for whatever you want. And this person said, I'm a poor man, if I can get rice. He said, rice is no problem. Then he said, just give me rice on the chessboard with the exponential growth, right? So exponential factor. So king said, no problem. And then very soon king realized that it is just not possible to fulfill his demand, because if you go up to the exponential or factor of 64, then obviously there is no rice left on this world, in this world to fulfill his demand. And this is what is happening currently. Our planet has resources only for 4.5 billion people, and we are already moving towards 10 billion. That means every second person sitting next to you is fighting for the same resources that you also have. So I think in this case, you have to really see that either we reach a new, because this infinite growth is not going to work. If this growth continues, anybody who has taken the first year class of thermodynamics will say such a system will be unstable. Even the very high entropy leads to ordering at some point, right? So what will happen? Either you continue and you are in an unstable state, or you have a crash. We know from supersaturated solution, you put a lot of sugar or sodium chloride and you stir it, and after some time you see automatically it will fall out. That's the spontaneous nucleation. That's the crash, the system is adjusting itself. All these things happening around, they are non-linear, but all of a sudden a tsunami, all of a sudden these are not changes. This is just the equilibrium that the nature is adjusting. I have a whole talk on that. I'm not today discussing it because that's not the focus. So we need to reach a new equilibrium, and that equilibrium has to go through a sustainable development. And with this, I think, in mind, even a non-scientific body like United Nations propose these sustainable goals, right? So these 17 goals, and at least many of them, you can have education and so on, but energy and health are the main drivers that are important for driving sustainable growth. So this is something that we need to think, that sustainable development requires saving resources and making more efficient use of resources. So with this in mind, actually, I served as the president of American Ceramic Society. It's one of the oldest society. So when I was, and every president can make some kind of strategic planning and emerging opportunity agenda. And my priority was that how do we define sustainability? Because I was also, and I'm acting as an ambassador in University of Cologne in Germany for sustainability. And I realized that everyone has their own definition. So it's almost like this story of an elephant and 5 blind people, right? So whatever you touch, you think this is what the elephant is all about. So with this, we started a new society, and I'm not making any advertisement. I'm just saying this is a society of, actually it's an alliance of societies. It involves a civil society also. There is no membership, there is no fees, there is nothing. It's just a common alliance of big society like IEEE, European Material Society, American Ceramic Society, American Chemical Society. All these big societies have come together. We have a steering board. I'm one of the founding members. Every 3 months, there is a webinar, high quality webinar. You don't have to attend it. You can also, at any time, it's on the website. If you can just note sfs.org, you will see, and it's telling you that scientific sustainability is not only about material science or engineering, it's all about ethics, religion. Everybody, every part of or small group of our society can contribute, and that's something I was not aware of. So I learned a lot of new things. I will just say that if you are interested, have a look at it. Now, this is more general. I will come back to what I actually was supposed to, otherwise Ivor will tell me why did we invite you. So I will, I'm a materials chemist by training. So we process materials by chemical methods, both as powders and thin films. We use them for different applications. They can be for like additive manufacturing, 3D printing, electrospinning to make fibers. We look at their functional properties in terms of like electrocatalysis, small molecule activation, hydrogen production. We look into catalytic conversion. If you are burning, we are working a lot on how can you create hydrogen from plastics, waste plastics or plasma, and then lithium and sodium ion batteries is an important area now. The common thing I think which we have is this processing. We really want to process materials in a very, very atom efficient processing. Atom efficient means high atom economy. That means whatever you take, you try to convert most of it into your final product, not losing too much. Like for example, if you do sputtering, if you make a thin film by taking, and I think there are a lot of, it's a physics building, so a lot of people understand what a laser can do. If you take a metal, gold, and you shine laser, if the energy is right, you can bring or atomize gold, you have gold vapors and then you can condense them. But in this process, 90% of your metal is lost. It goes everywhere in the chamber. You may get a nice film, but you have a very poor atom economy. So how do we convert this? That we try to make a process which will give you, and this generally is done by making a metal organic compound that is, and this is how semiconductor industry is working. They work with all metal organics, whether you look into silicon germanium semiconductors, you look into 3-5 semiconductors or 2-6. Without metal organics, many of the high-end semiconductor technology will not be. So we did this, we started long back, and I'm not going into detail, I'm just telling you in one slide. We do this, we make our libraries of precursors. We have used entire periodic table here, and we look into their kind of behavior in terms of volatility and stability, handling. Shouldn't be too toxic. They should be stable enough for having a shelf life and so on. And then we look into their functional properties, and my group is doing for a long time both. We do coatings. Coatings can be done in two ways. You take a substrate, you implant something, and you have just changing the top layer. Like this is how you make stainless steel, right? You take iron and you put on the top layer some carbon, and then it becomes corrosion resistant, and then you say it's a stainless steel. Now you can do this way, or you can take a material and coat something on it. Like you have silver, you can put a gold layer on it then. Or you can put a rhodium layer. So you can get a lot of ornaments where you have these, where the surrogate material is a little less expensive, and the top you have the most expensive, like platinum coating and so on. And then we look at the catalytic properties. How does this look like? And I'm just giving one example. This is for the bipolar plates. This is a Korean car company for which we have worked recently. And what we did, we made these thin films for their solid oxide fuel cells, these techs. And the idea was, currently they use a lot of noble metals. All the catalysis is based on silver, platinum, rhodium, palladium, which are very expensive. How can you reduce the loading of these noble metals? So one idea was to give a highly conductive carbon matrix. And we know what graphene is interesting because it has a very high conductivity in the plane. So if you can make a very metal-rich carbon matrix, this is what we did here. And the other approach to the same is now using powders. Right? You do the powders. If you take a ceramic powder and you put it into solution, it's not going to work because a solid will just settle down, right? So you have to make it intractable by creating a surface functionality. And this was among one of our first patents on how do you modify solid with small molecule conjugation. And if you have molecules which have two functionality, one side they are conjugating on the particle, on the solid, and other side is now open for a matrix, so you can put them into polymer, polymerize them, and this is called small molecule surface modification, or on-solid chemistry. So basically, it's a conjugation chemistry on solids. And we use this in different areas. I'm not going to talk all these. One is about, can we make these catalysts useful for small molecule activation? Can we like split water to create hydrogen? Can we activate nitrogen to create ammonia and so on? Solar cells, batteries, and also mechanical energy harvesting by piezo. As I said, I will not go into many of these areas, just want to give you one example each today. So it's about small molecule activation because this is a very important area and chemists understand this very well. Nature is doing, we look at nitrogenase. Nitrogenase is something which is used for nitrogen fixation. Or you use photosynthesis. If you go on this beautiful campus, see everywhere, every leaf is a reactor where you see that the water is being split and you create oxygen and that's coming to us and you use CO2 as the input. The only issue with many of these chemical reactions is that when you activate something, otherwise it will be a spontaneous reaction, right? So if it is waiting for somebody to come and do this reaction, there is an activation barrier. That means it has to go over a barrier so that it can be catalyzed, right? So it can be turned, if you want to turn A into B, there's always an intrinsic energy barrier. This is what we call as activation energy, right? So the adducts or your starting material on the left has to have less energy or free energy compared to the product. So if the free energy or delta G is negative, then only this transformation will be allowed, right? Otherwise it will go back. So this is something that we understand, and it can be, obviously, you can say, okay, I'm inspired by nature. So if you look around, nature is doing it for many years, but the only issue is nature is not very efficient, but nature compensates it by a huge biomass, right? So we cannot compete with nature if they have 1 or 2% of efficiency. But if you want to make a cell which is doing this chemistry and it is having 2% efficiency, nobody will buy it. Because if you are even putting a photovoltaic module on your rooftop, it's a small module, right? So you don't have a space like of a football ground. So you want that small device to be very efficient. So I think if you see here, you can do it in lab. Probably this will work. It's not working, it's fine. Right, so you can do it. This is now a first-year experiment where all students are doing. You take titanium oxide, you shine light, UV light, you create electrons and holes, and you can split water, you have enough hydrogen coming out. Now, this has made catalyst very, very important, and people remember the process, but they forget everybody will talk about carbon-carbon coupling. So no, if you see around, so many Nobel Prizes have been given for catalysis, right? So I'm just going through very quickly, and because in the last one, this is in my own department, so Benjamin List on carbon catalysis. So if you talk to them, they're obviously working on different kind of reactions. But what is catalyzing is, the catalyst is important, but people forget it. So I think that's where ceramics and inorganic catalysts are coming. Most of these are driven by metals. Okay, Ben List, he did on carbon, but otherwise everywhere you have a metal involved, a metal oxide involved. Look at the ammonia synthesis, Haber-Bosch. Ammonia synthesis got 3 Nobel Prizes. And the last one, Gerhard Ertl, it was on how nitrogen is being activated on the surface. So this is an important point. And this is where I think I spoke to some of the students who were working on hydrogen evolution reaction here, I think with Professor Unas, or in your group probably, I think it was. And it was very interesting to hear to these students that they were all working on this hydrogen as a green fuel. And it is a promising vector. So I agree with that. The only thing is that how do you make it really green? It is that today hydrogen's demand is 80 million ton, right? And it will grow to more than 500 million ton per year. If you want to produce so much of hydrogen just by electrical energy, that means taking 2 electrical leads, electrochemically decomposing water, it will consume all the renewable energy that you have on the planet. So this demand of 15 petawatt to run an electrolyzer is a materials challenge. You cannot engineer, first of all, so many electrolyzers. And secondly, it's also very energy intensive. So that's why the green hydrogen, then the European Commission started 20 years back, was this idea that, okay, the best abundant source is sun, and the other abundant source is seawater, not the sweet water, which we have very little. Seawater is the one which you are not going to drink. It's saline, it has electrolytes, and you can use it to split water. Seawater, we all know when you go to the beach, you can't stay there too long, you start feeling that it's itchy. Why? Because you have all kind of electrolyte dissolved. All kind of chlorides you have, all kind of even other minerals are there. So this is a corrosive environment for electrodes. So there is a technology out there. Electrochemical hydrogen production is not, you don't have to now use Maxine or some kind of MOF for the millionth time. There are simple materials already existing. You can take, for example, 2 metals. These are mostly noble metal once again, but this is a commercial technology. So these electrolyzers are on the market. And the only challenge is that if someone tells, or Vilnius University decides that we should order 100 units, it's not possible for a company to deliver them because the material scarcity is there, materials challenges, because you have to engineer this. They come with a guarantee of 10 years, but the amount of equipment that you will need will not be delivered on a short notice, and globally, that's why not possible. The same thing is with everybody driving an e-vehicle. It's not going to be a realistic scenario because we don't have so much of lithium, not so much of anode or cathode material. So I think that's a real challenge. So people have looked into different kind of oxides. It's a very simple reaction. You take a semiconductor oxide, which is good because oxides are very stable. If you see what has survived our evolution are the rocks. So oxides are good material. The only thing is oxides are very lousy conductors of electricity. That means charge will not transport. They don't have the needed dispersion of the bands and so on. So there are no well-defined pathway for electrons to transport. So people have looked into a lot of different areas. They have looked into different materials. And then they realize that it is very difficult to find one single material which will give you the photovoltage that is needed to split water. It's not much. Theoretically, it's only 1.23 electron volt, but in a solution, if this is your reactor and you put two electrode inside, you will need 1.5 because you have a resistance. Ions have to go from one side to the other side, and this diffusion barrier is imposing a penalty of 0.2, 0.3. So in reality, you need 1.5, 1.6 volt that is needed to split water. But it is increasing. If you see the green curve, it is becoming, so green hydrogen is becoming very competitive, but there are still challenges. And the challenges are to make the materials which are cheap, abundant, so less expensive. I don't really like the word cheap, but less expensive. And they are really made by some industry. So I coordinated this European project on solar hydrogen for seawater. And we had Siemens, is a German company, Siemens is making electrolysers, so they were interested, and we had BASF is making these pigments of iron oxide, and we looked into iron oxide, and a lot of people are working, and we came up with a lot of calculations and so on. This is an old story, so I'm not repeating it. It's published here. As you see, it's almost 10 years old. Then we realized that by using this combination of iron oxide and titanium oxide, so titanium oxide is your capping layer, which is absorbing UV light, and then you have beneath iron oxide, which is now absorbing invisible light. And this combination gives you a very good catalyst, very good photoelectrocatalyst. The problem is, as I said, they are not very good conductors, so at the interface, you will have a lot of charge accumulation. So here we use graphene. You can just put a small layer. You don't see, obviously, graphene, a single layer between iron oxide and your substrate, and you can increase the water splitting. So this is something that works. Now I will jump to, when we did all the study, Siemens did what is the cost if you are producing it by using a solar field of 100 by 100 square meter, and we realized that it is not going to work with a single material. You have to provide some bias. The imagination or the expectation of European Commission was bias-free. That means only sunlight splitting water. That's not going to work, so you need, and now if you see around, research is mostly on tandem PV-PEC electrolyzers. We just published a review with our Chinese colleagues who are doing amazing job on solar hydrogen production. And this is very interesting for European economy. If you see one electrolyzer, which is this is the world's largest electrolyzer. This is installed in Norway. Now you see this size, and it looks very impressive. You go on the website, you look into the detail, this electrolyzer was manufactured in China. Because in Europe, we cannot manufacture this size, right? That means this is already a bottleneck. If you want to install several of these, that's something which you have to think in your business model. Because having a prototype is not going to solve this problem, but I think this is a possibility of making now photovoltaics, and a lot of things are happening. We have cheap photovoltaics. So I know this perovskite, which was discovered, I will say, 15 years back by Miyazaki. And we have been also working, I'm not talking today, 3 of my students, they are running a company. This company is now doing very well. They are making, now for carports, they are making photovoltaics for carports, so that if you have an electrical vehicle, you can charge your automobile by using this carport. So this PV setup can also be used for electrolysis. But still, there are 2 major challenges of green hydrogen. One is that the other half of the reaction, because in hydrogen evolution, people think only hydrogen is coming out, but you have 2 reactions. When you split water, you are creating hydrogen and half mole of oxygen. And oxygen evolution reaction is actually more important, because that's 4 electron transfer reaction, and that is, if it is slow, automatically your hydrogen evolution will be slow. And second thing is, what do you do with hydrogen? Why don't we have hydrogen in the nature? Because very reactive. So you need to have an immediate use of hydrogen. So the chemical conversion is needed. Now, I think there are some fundamentals. I will just skip that. The main thing is oxygen, and that's why you have a lot of interesting things in nature. Oxygen is one molecule which is not having, which is in a triplet state, right? So it is, singlet oxygen is very reactive. So if our oxygen will be singlet, it will be very difficult, because we all are breathing oxygen. So we need to make sure that we have oxygen, which is now, and if this oxygen is there, it's not oxidizing anything. You need singlet oxygen if you want to, for example, do a chemical reaction. If you want to use that oxygen or hydroxyl that you are producing, and you want it to react for oxidation of, say, for aldehyde or whatever reaction you want to drive, you will need something which is in the singlet state. So there is a spin barrier. If you want to take this triplet state and you want to convert it into, you want to do a spin inversion, which is necessary for a chemical reaction to occur, you have 1 electron volt of spin barrier. And that needs this extra energy. And at this point was the question, how can we make materials better? And I told this long story of iron oxide just to, how can we make now materials better? Because when you say a catalyst is dead, it's actually the surface. So we started something new, and that's, I think I'm coming towards this 2 example. One thing is to make materials now in magnetic field or field. We do synthesis in our typical parametric space using temperature, using pressure, using different solvents, microwave. Field has been less used. So we applied magnetic field because iron oxide is it's an antiferromagnetic, but it still has iron 3, which D5 center. And what we found out is that by having magnetic field, you can control a lot of things in the material by applying magnetic field. You can control the atomic scale ordering. You can promote certain facets on the surface. And that is something which is helping the catalyst to survive for longer time. I will show you the example. And we worked for now almost 8 years now. We have learned that a magnetic field, which has a very little energy, it can change the spin orientation on the surface. It can change the texture, what facets are exposed. It can help in phase transformation, texturing, and faceting. And we did this for iron oxide. It's 2 detailed study. It has appeared in Advanced Energy and Sustainability Research. What it shows is that if you grow a catalyst in magnetic field, it is not degrading, whereas the one which is not deposited, same material, because now you can control the grain boundary. You already make the catalyst in a preferred, more stable state. And this is what we have looked into detail. What is happening when you're applying magnetic field? One thing is that you promote the diffusion of ions. Field is promoting, so you have larger domains. Larger domains means the volume fraction is decreasing, so you have less grain boundary resistance. We did this by, you can do impedance spectroscopy, and these studies are telling you that you have the number of inactive states, because on a catalyst surface, you can imagine there are like stools. These are the sites where the molecules can come and sit down, and then you see that these molecules are being activated. So these states are not all active. Some are active, some are not active. And these can be also changed by. So we did it. Now it's running for several weeks. We saw that these kind of catalysts, they can survive for longer time for the same reason that you have a magnetic field engineered catalytic surface. Now, iron oxide is good, as I said, that you have to make it better. And this is what people are doing by doping. You take the lattice and you add something which is having either a different valency so that you have an electronic disorder. And you can do it. So example, you can put nickel in that. And you see that by looking at the magnetic studies, that the magnetic memory of that material is now changing. Because you are having now different domain structure in the, so the coercivity values are changing. And this you can do, it's a generic thing. You can do it for cobalt ferrite, magnet ferrite, and this is just going to appear in advanced functional material. And you see that from the hysteresis and remanence values that the material which is deposited in field, and these are not very high field. 1 Tesla is not, if you convert it in terms of temperature, it will be like 3 to 5 degrees centigrade. It's not a huge amount of, but you can see that it's helping us. If you look at the Faradic efficiency of these material, this was for ammonia, the material which is deposited in field has very, very high values. So now we have a method to make more hydrogen. What do we do? And that's where I think and this is not that only we, this is the roadmap that most of the community is following. They said, okay, this hydrogen, if you can use it, one chemical which is taking most of the energy. Who can tell in this younger audience who are taking chemistry classes? One chemical which is taking almost 1.5 to 2% energy of the world. Simple molecular. Anybody? It has nitrogen in it. Very good. Yes, I will buy you a coffee. You are So ammonia, because ammonia is needed in fertilizers. Ammonia is actually responsible that today everybody can get food everywhere. We still have poverty and hunger, but ammonia provided the basis of fertilizers. It is also a commodity in polymer industry and ammonia synthesis. So I think you see it here. It's now ammonia technology is so old. Ammonia storage is no problem. Ammonia consumption is no problem. Ammonia transport is no problem. Hydrogen has all these problems. Hydrogen you cannot store. There's no material where hydrogen will not diffuse. It's such a small molecule. Hydrogen is very difficult also to condense. You need a lot of energy. So why not to convert hydrogen into ammonia? Now the problem is ammonia needs nitrogen as counterpart. We have 78% of nitrogen everywhere here. 78% is filled with nitrogen. But it is such a satisfied molecule. It's happy-go-lucky. It has everything. It has 8 electrons. It has triple bond. It is not interested in going for any chemical reaction. But there are people who are smarter. So you have ammonia as energy carrier. A lot of people are using. I have seen this car 2 years back myself. This is working on ammonia fuel cells in Guangzhou. This is a collaboration between China and Japan, so Toyota and GSE. And obviously, Japan is using it for 20 years. They are using ammonia for the marine sector as a fuel. And the entire Green Deal of European Union, the Green Deal paper was written in collaboration. In collaboration, basically, we got inspired. I don't want to say we copied, but we got inspired. So the entire, because Japanese were much ahead, they started this. And now, and I was very happy, just you can see it's 24. The first plant for electrocatalytic ammonia synthesis was opened in Denmark. That instead of going from Haber-Bosch needs very much energy. It was these two gentlemen, Haber and Bosch, they developed, and BASF is surviving that. Big reactors, high pressure, high temperature, because you need this to activate nitrogen. And chemistry is not only about kinetics, it's also about thermodynamics, right? And that's why you need this combination of high pressure, high temperature, because there is a huge barrier. It's also kinetic barrier. So that's why you need new catalysts which can activate nitrogen. So there are a lot of compounds. I'm just giving you one example because this class of, you need now 2 metals which are cooperative. One is activating nitrogen, the other is receptive towards hydrogen, right? Because when you are activating nitrogen to create ammonia, you do it in water. Because nitrogen gas, you are back to Haber-Bosch. You do it in solution, and in solution, water will electrolyze first. So all the electrons that you are giving in your reactor will be consumed by water to create hydrogen, and you have no ammonia. So you have to stop this reaction. And that's something that you can do. I'm not going into detail. Nana, she has done some amazing work on that. She showed that these pyrochlore compounds, this class of compounds is called pyrochlore, 2 metals. And the idea here is that one is closed shell, so it's not going to very much ready to interact or change the oxidation state. So she used zinc and vanadium. Zinc is the D10, is stable compound, iron, and vanadium can go in multiple oxidation state. And zinc is forming a very stable hydride. So you have attachment of hydrogen on zinc, and then it activates the nitrogen. So I think, no, I'm sorry. So once again, that's the problem when you jump on. You have vanadium, which is picking the hydrogen. So vanadium hydrides are formed as terminal, and then you have nitrogen activation by a mechanism that we have looked into all details to show that by DFT also that you have a side-on activation because both the nitrogen, so basically nitrogen is coming like a dumbbell and sitting on 2 hydrogen, and it gets activated and that's the first step, which is very, very energy intensive. We did very detailed study, so in the interest of time, it is published in ACS Catalysis 2026, so it's a recent paper. Because on the surface, it's always a challenge. If you publish a paper, people say, how do you know this? So surface enhanced infrared, which is called CIRAS, tells you what species are formed. Now this is one way. What we see is that once you have this catalyst, it's becoming now saturated at some point. And that's the problem with most of the catalysts. They are saturated at some point. And how do you go around? I said we have to look into new processing, and there is a new area coming up. It's called piezocatalysis. Piezo-catalysis is just taking a piezo material, and I think you know what piezo material is. It's basically you apply mechanical force, you displace charges, and you create a piezo potential. Now, if you can do that, your surface is polarized. And on a polarized surface, you can even polarize a molecule like nitrogen, because you just need a slight fluctuation of the electron density, and that's enough for a chemical attack. This is how the entire chemistry is working. When you look at the collision theory, if the electronic cloud is little bit delocalized or displaced, you create transient dipoles. And this is where when the molecules get activated. So Naina, in her PhD, she is now working on this. What we are doing is taking a piezo substrate, putting catalyst on that, and mechanically actuating it. And by doing so, you convert a classical electrochemical cell into piezo. You can see that it's very fundamental. You basically have a mechanical actuator here, and this actuator is then helping. At some point it will come, I was told, yes, yeah, so here. So now you are having continuously vibrating electrocatalyst. So condition is that the electrode is really fixed, it's not falling in the solution, and then you can create small piezo potential that again helps you to have a better catalyst. So this was the first story I wanted to tell about the small molecule activation. The second is about small molecule delivery, and I see I have a clock in front of me. I have only 15 minutes. I will quickly go. I showed in the beginning that you can do a lot with nanoparticles, nanopowders. And the second thing is more about, I will jump few slides. We worked on hydro. Is that how do you work with small particles that are now in solution, right? So you can, that's an advantage. You make a solution, you can spray it. You can do coating, super hydrophobic. So this was a project of one of my PhD students to make high temperature super hydrophobic coatings. They are highly needed for energy saving, because if you have, and I think in Lithuania, you have also a lot of snow. So if you are flying, you know that sometimes you have to wait till the planes are de-iced. You have to remove. A lot of chemicals go. So if you can somehow inhibit the nucleation of ice crystals, you can save a lot of energy. So there is a big interest in this high temperature hydrophobic. Please remember this high temperature. Room temperature hydrophobicity you can do with any organic. You can take a perylene coater, you can take a silane, and you have a hydrophobic surface. Hydrophobicity is stable at higher temperature. So this is still that's why I'm saying 300 degrees is a world record. So we were very happy to have this. And it was done, and just to show you this video, on the left side, it is the coated side. You put it on boiling water, and you will see there is no condensation of water. On the right side, on a normal glass, you will obviously have water droplets being formed. And this super hydrophobicity, and it was funded by a German company. It's a glass company. The name is Schott. And Schott is actually looking for the kitchen appliances, because once in a while when you are cooking, then you see that, I'm saying once in a while because students don't cook every day. So you see that if you are dropping ketchup or mayonnaise, you have a charring and you have a black residue, right? So how can you remove it quickly? This super hydrophobic surface, which is stable up to 300 degrees C, is very helpful, and they want to put it on their products like Ceranfeld and so on to have an easy to clean surface. And it's interesting that when you do all these, we file the patent, and then the European Union comes and they said, no PFAS. European Union said, you cannot use polyfluoryl alkyl substance in Europe in any new technology. So what do? Then you go back to your classroom books, and then you find out that there are materials where you don't need fluorine. And I think Professor Karaiva, he's working for a long time in these materials. These are lanthanide oxides. They are F element, so F orbital elements. What do they signify, or what do they tell us? That the F orbitals, they are so low lying, they will not form easily a bond with hydrogen. And if there's no hydrogen bond, then you will also not have any hydrophilicity. So they are intrinsically hydrophobic. And this was a paper, a theoretical paper from a group, and it was in Nature, saying that these materials should be intrinsically hydrophobic. And then we did this to show. So we learned that you can make these oxides. Again, you need a precursor chemistry. So we then moved this chemistry to design new drug delivery application, right? So this I will, next 5 minutes, just talk about. I told you in the beginning that today, when we take a pill, it goes everywhere in the body. The reason is that the drug delivery has a lot of challenges. For healthy body, for a headache and so on, when you take aspirin, it's no problem. But for tumor, it's very difficult. So what I have learned in my 15 years of research with the medical people is that this term was new for me, undruggable sites. So a tumor is a site of where the drug molecules will not stay for too long. So because tumor is very complex, it's very heterogeneous. And if you see what happens when a drug goes on, you can see on this mice molecule very nicely. If you put drug inside this mice model, so this mouse, and you record it by an infrared spectral imaging, then you see that most of the drug goes into larger organs. Larger organs are the sink, right? So what do you do in this case? Because and you can see this, in 5 minutes, all the drug will reach, this is the time scale here. In 5 minutes, you lose most of the drug. That's why we take so much, 400 mg, 800 mg. A lot of people say, I need minimum 600 mg, otherwise it will not work. It's nothing to be proud. It's actually, all the pharmaceuticals, they are toxic molecules. They work just because they are cytotoxic. They kill the cells. So how do you reduce the amount of, maybe you need only 1 milligram, and you are taking 600 milligram. Because the probability, 99% of the drug will just be flushed away because it's a passive diffusion. It's just, so how do you make it better? One possibility is that you really come up with a new formulation method. So I will say that if you look, there are a lot of things which we can discuss. Molecular drugs, they are popular in the chemical industry because they are easy to make. Once you have a new molecule and you say, okay, this small modification giving me more potency, and then you can just modify it and you can scale up. But the formulation, the drug formulation is, when the first drug was made 150 years, you still do the same primitive way. There is no way to make, you just put an excipient, the active pharmaceutical ingredient, you press a tablet, and that's it. So you can keep it in a fancy box, everything, but the chemistry is very, very primitive and unchanged. So how can we change it? And that's, I think, and this was a very nice review by Bob Langer at MIT, and in Nature reviews for drug discovery, where they said that we have to change this mindset of drug formulation. There are a lot of advantages why there is inertia in the industry, why industry is not changing because of all these commercial reasons. I'm not going, but the future is of making now drug inside a carrier which is intelligent so that it precisely deliver where it is needed, right? So that is very, very important, that you find maybe an Amazon for your body that delivers the drug which is where it is needed. And there are a lot of things you can do. This kind of compounds, we all know, the lipid nanoparticles, because in pandemic, we got to know that microRNA technology was there. It was the encapsulation of microRNAs in the liposomes that gave us the vaccines. There are also inorganic particles, especially gold, silica, because they are non-toxic. And obviously, they have different circulation time in body. Organic matter will decay faster. Inorganic will stay longer. So, and one approach is now to mix them, and that's what we are doing in Cologne. We call them, if you mix liposomes and ceramics, you come up with something which is called cerasomes. And the good thing about cerasomes is that most of the problem of the drugs, these molecular drugs, this is for kidney, is that they are hydrophobic. When you take, your body is hydrophilic. That's why sometimes when you take drugs, they are in a very oily suspension, because these hydrophobic drugs cannot be dissolved easily into water. So these cerasomes, they are allowing you to take both hydrophobic and hydrophilic. And the current trend is co-location of drug. Sometimes by having dual action drug, that means two types of drugs for the same tumor treatment can be more effective. And this can be done by this approach of cerasomes. We did this, we have very active collaboration that how we can now formulate drugs in these new capsules, new nanocarriers. And I'm not going in the interest of time in many details, but you know that liposomes can be made very easily. You can encapsulate one drug, but they are organic bilayers. They are dynamic. If you remember during vaccine, that was the problem of cold chain. You have to store the vaccine at +5 degrees or at 0 degrees. because at room temperature, these bilayers will just open up and your drug will be lost. So that's where you have to now think of a small nanoparticle, a nanocarrier where the drug is sitting. How do you take it to the tumor? And this is something which we did recently on triple negative breast cancers. This is triple negative because you don't have the possibility of delivering the drug to the tumor due to the absence of cell receptors. So what is happening if you have a cell is having, on the cell walls, there are receptors sitting there. When a drug molecule is coming, these are the point where the molecule can dock. So if you have your carrier, it should have the affinity ligands on the surface so that it can go to the cell and be internalized. The drug will only work when it is internalized, right? So this is something that we have shown that by encapsulating drug, you need, in this case, this hormone. This is estradiol. This hormone is needed to really have a targeted drug delivery. In this case, the microtumor environment has the possibility, because it has higher pH, you have this drug going through the carrier in the molecule. And in contrast to what is known, the current therapeutic index is 0.7%, but through this new encapsulation in nanocarriers and having a target ligand on the surface, you can have a much better drug delivery. Okay, so I think with this, I will come to an end. Before ending, I would like to also show a fun experiment. So we were doing this drug, and one of the master students, she came and she said, can we do something for the same? Because, you know, drug tests, they take very long time. You need to have somebody. So she said, why can't we use these small molecules or these carriers to make green walls? Because this was a new priority program in German Science Foundation. We have so much of concrete, and to cool this building, you will need a lot of air conditioning. So if you have now on the concrete, if something can grow, and this was actually, it started in Singapore, if plants can grow, all right? So, and second thing is if they can also metabolize all, you don't have here any pollution, very good to be here, it's a pure air, but in countries where you have a lot of pollution, you see that this concept is coming up of the green wall. The green wall is nothing but you can put a concrete on the surface, and the idea is that can you grow now small plants to sustain. These plants don't have big roots, thick roots, so there is no danger to your concrete. So I think she did amazing work because she was in Singapore and she saw it everywhere. That in Singapore, all the buildings are having these vertical gardens. What they have in Singapore is that actually these are hanging gardens. They are not attached to the surface. And this new idea is that can we have a direct growth on a concrete? So it's called bioreceptive cement or bioreceptive concrete. And this is interesting because this worked. We did the same thing. Instead of drug, now you can take urea or phosphates, and then you see that, okay, it's working, and you can grow plants on these. So it's a new area to work on, but it's very interesting. So I think with this, I would like to finish. I will not go into any. I will conclude by saying that I showed you two things. One is that in terms of energy transition and health transition, the understanding of new materials is becoming very, very important. Nanomedicine is helping in new drug formulation, in having stimuli responsive, because if you have something which is inside the body, if you can activate from outside or from the local environment, it can be hydrolysis, it can be a pH change, it can be light therapy, it can be field. That is very helpful. Even we can have a radioactive tracer. Second thing is that the electrocatalysis, and if you can combine it with to make photoelectrocatalysis is a very sustainable way to activate small molecule to create energy carriers. And I think this is the final thing, that if you look these small molecules with CO2 to produce hydrocarbons or water to produce hydrogen, and then use hydrogen for ammonia, you have a good loop. And we will always have these small molecules. We cannot get rid of these small molecules because the chemical industry, we talk about CO2 made by human beings, but 85% of the CO2 impact is coming from chemical industries because they have no other way than to use these. Second thing is that we need innovation, and that's why I'm saying as a chemist, I'm proud about chemical innovation, but aspirin, and today, as I said, that we still have this condition, what you see in the left side. If you take a pill, this is what is happening in your body, drug going everywhere. The future is this precision therapeutic, that it goes where it is needed. Not personalized medicine, it's precision therapeutics that is, and that's why it has to change. And I'm saying tablet pressing is still the same old science that was 100 years back. Okay, with this, I think I will thank you all for listening to me. I see that it's 12. I would like to thank my group for doing most of the work, for funding agencies, for providing. And I'm very happy for this opportunity for being here in Vilnius. And thank you once again for us, and would be happy to take any feedback. Thank you very much.
So we have time for questions, please, if anybody, any questions?
So probably you can add some discussion regarding those three technologies. I mean, hydrogen, ammonia, and hydrocarbons.
Yeah.
The slide number 114, so
Yeah.
far as I remember. I mean, which one will, let's say, probably most popular after 10 years, and let's say for next 20 years will be most probably most popular, according to your opinion, of course.
Yeah.
Thank you.
Thank you very much. I think that this is a very important point. We see that after 20 years of funding in hydrogen, we are realizing that it's not that easy, it's not that green, because splitting water to create hydrogen in lab is one, but to make it a scalable technology. So this big barrier of scale, it is related to every new discovery in lab. But in terms of what could be a promising approach, I think nitrogen, not only that it's lot, you also have lot of NOx and so on. So you need to find ways to metabolize the pollutants, and you have lot of nitrate in the soil, in the waters, in the fisheries, because this nitrate composition. So I do a lot of Indo-German projects, and in India we have a big project that is how to use nitrogen-rich water. If you can reduce the use of urea, which is a big, then you can do it by taking nitrogen, using plasma electrolysis. So you make a nitrogen-rich water, and with this you can irrigate your field. The problem is that you cannot provide it to every farmer. It's going to be very expensive. But that is the approach of like reducing. Nitrogen has a much more potential. The spectrum is very wide. You can use ammonia directly as a gas, as a commodity. It is used directly as a fuel, and you can make many more chemicals with ammonia. And in addition to its storage life, this is going to be definitely a winner at the end, because the nitrogen reduction reaction has a huge barrier, and whatever catalyst overcomes that, it will directly go to industry because the industrial technology is there. The electrolyzer technology is also there, but it was there before we started green hydrogen. And that time already people should have considered that the problem is the scarcity of materials, the engineering of the goods. Like you don't have all the reactors there. And just to young folks here, if you have an electrolyzer, the one electrode in these commercial electrolyzer has 10 kilogram of silver as electrode. So it's very expensive, and it's obviously it's being used, and because the silver is slowly consumed, it can be recycled. And that's why that's a limitation. So if you want to provide just this country hydrogen, you will have a lot of challenges. So that's my take on that, but the discussion will have many more facets. Sure.
Any more questions, please? Yeah, please.
So I wanted to ask about these fuel cells that could utilize the ammonia.
Yeah.
What type of fuel cells could we use, and are there any material challenges related to that issue?
Very good. Thank you very much. I think this is either you're working, because this is the current upcoming area, that if you have ammonia, the first thing is if you want to burn ammonia to get hydrogen, then also you need burner where you don't have a reaction which will corrode your material, right? Same is with ammonia fuel cells. So currently, because you have a combustion happening on the ceramics, so currently people are facing a lot of challenges. The materials that are being used are all perovskite. So most of the ferrites, orthoferrites, and they all react with nitrogen to make nitrides. So you basically degrade after few 100 cycles, your electrode completely. And this is the challenge of making these solid oxide fuel cells based on ammonia. And we have a project. It was just funded with Singapore. And we are exactly looking into this problem. It just started that how do you tune the interface so that your nitrogen decomposition becomes efficient and nitrogen is not becoming part of the lattice. That means you are not ejecting oxygen out and having nitrogen in. Yeah. So nitrogen should go as a gaseous nitrogen. That's a good point, yeah.
Okay. So let's thanks once again for nice talk.
Yeah. Thank you.